Do you want to build fast, reliable software that runs like C++, but without memory bugs or mysterious crashes? Sounds like a dream, right? Actually, no. Welcome to this Rust crash course. In under an hour, you will learn how to write real Rust code, the same language used for building WebAssembly modules, high performance servers, and even parts of Firefox and Dropbox. Whether you are coming from JavaScript, Python, or C++, this tutorial is for you. No prior Rust experience needed, just a bit of curiosity and a code editor. By the end, you'll know the core concepts of Rust, understand ownership and borrowing, and even build a simple project using Rust, all from scratch. Alright, so let's get started with Rust on your machine. First, head over to rust-lang.org and click Install. From this page, select the option that best suits your machine. This gives you rustup, the official installer and version manager for Rust. Pause this video, let installation complete, and then resume. Once installation is complete, open your terminal and type the following command to confirm the installation. If you see a valid version number being displayed, this tells us that Rust is properly installed and you're ready to code. Next, I must introduce you to Cargo. Rust ships with Cargo. It's powerful build tool and package manager, kind of like npm for JavaScript or pip for Python. Let's use Cargo to create our first project. This creates a new directory called hello_rust. Let's go in and run the project. And you can see hello world being printed on the screen. So behind the scenes, Cargo created a main.rs file in a source folder. That's your starting point for writing Rust apps. Let's take a quick look. I have Visual Studio Code installed, a powerful free code editor from Microsoft, which I'll use throughout this video. You can install it from code.visualstudio.com. Code.command opens Visual Studio Code in context of current folder. Let me browse to main.rs file. What you're seeing now is your first Rust function. fnmain is like int main in C, the entry point. Println followed by exclamation mark is a macro that prints to the terminal. The exclamation mark tells us that it's a macro, not a normal function. If you want to follow along, open your terminal and code with me. No fancy setup is needed. Now that you have run your first Rust program, let's talk about variables, the building blocks of any program. In Rust, variables are immutable by default. This means once you give variable a value, you can't change it unless you explicitly say it's mutable. That won't make sense until I come up with an example, so let's do that. Okay, this defines a variable x with a value of 5. The let keyword is how you create variables in Rust, similar to let in JavaScript or var in Python. And println lets us print it to the terminal. Note in the println line, the curly braces are a placeholder. They get replaced by x. And there can be more than one curly braces in a println statement. Okay, that's not our main focus, so let's get back to x. Now, what happens if I try to change x? I say, let's do a cargo run with this code and see what happens. And immediately you will get a compile time error saying cannot assign twice to immutable variable x. So here's what you need to know about immutability. Rust forces you to be clear about your intentions. By making variables immutable by default, it helps prevent bugs, especially in large or concurrent programs. If you do want to change a variable, use mute. So it sounds like mute from mutable. Let's give it a try. And this time it worked. Mute stands for mutable, which is an explicit instruction telling Rust that this value can be changed. Rust is statically typed, which means every variable has a type, and that type is checked at compile time. Most of the time, Rust figures out the type for you. Like in this case, it figures out it's a number. But you can also write it out explicitly just like in TypeScript. Alright, here i32 means a 32-bit signed integer. Rust has other number types too, like u32 for unsigned, f64 for floating point. Now let's talk about something cool, shadowing. Let me type some code that will make it easy to understand. Alright, now note that this is not mutation. We are actually creating new variables each time. We are redeclaring x, not trying to change value of x. Shadowing is useful when you want to transform a value in steps without mutating. In our code example, you are actually saying make a new x based on the old one or even with a new type. Simple takeaway being adding mute to declaration lets you change a variable, but shadowing allows you to make a new one with the same name. Shadowing lets you transform values step by step, like trimming, parsing, or converting types, without introducing new variables names like x1, x2, temp, etc. It keeps your code clean and readable, especially in short functions or data transformations. Let's do a quick comparison with other languages you might be familiar with. In JavaScript, variables are mutable by default unless you use const. In Python, most things are mutable unless they are a literal or explicitly frozen. And in C++, variables are also mutable unless you mark them as const. Rust flips the default. Variables are immutable, and you have to explicitly say mute if you want to change them. This means less accidental mutation and more predictable, safer code. So in this section, you learned how to declare variables, how to make them mutable, how to annotate types, and how shadowing lets you reuse variable names. Next, we'll look at control flow, if, for, match, and more. So now let's talk about control flow in Rust, the if this, do that logic in programming. Rust control flow is powerful, expressive, and very familiar if you have used other languages like JavaScript, Python, or C++. Let me type something and then I'll explain. Alright, nothing really surprising here. Rust if expressions work just as you'd expect. But here's something cool. If is an expression, it returns a value. Let me show you. Okay, let's run it. And you see value is 10. Because if returns a value, you can assign it directly to a variable. But the branches, like in the if else statement, must return the same type. Otherwise, the compiler will complain. Now let's look at loops. Rust gives you three main types of loops: loop, while, and for. Let's start with loop. Right, so loop is an infinite loop. It runs forever until you break it manually. You can even return a value from a loop by doing break 3. Or in fact, let me do another example. Okay, here we go. The count 1, 2, 3 is from the first loop, and the result is 42 is coming from this part. I hope this is clear by now. Right, let's move on to while loop. We type the example first as before. Okay, pretty much what you'd expect from other languages. It runs while the condition is true. And it's 0, 1, 2, 3, 4, and when n is equal to 5, it breaks. All right, our last loop is for loop. So let's type out an example as well. This loop prints 0, 1, and 2, and the syntax 0 dot dot 3 is a range like Python's range 0, comma 3 or JavaScript's for loops. Rust for loop is safe and avoids index out of bounds errors. It's the preferred method for iterating over collections. The last control flow I would like to cover for Rust is match. It's like a more powerful switch found in other languages. Pretty straightforward, right? The underscore wildcard acts like default. It catches anything that doesn't match. You can match on values, enums, or even complex patterns. We'll go deeper into match later when we talk about enumerations. Right, so to recap this control flow section, you saw if, else, and expression-based conditions. You learned loop, while, and for, and you got a sneak peek at match for pattern matching. Next, we are going to talk about functions and ownership basics, the heart of what makes Rust unique. Okay, now let's dive into functions and then look at the most important idea in Rust, ownership. Why is Rust memory safe without a garbage collector? It's because of ownership concept. But first, let me get rid of the stuff that we have been stuffing in main because we hadn't learned functions by now. So let's replace it with a call to a greet function and give some name, something like Rustacean. And let's write a greet function. Okay, here we define a function greet that takes a ampersand str, a string slice, and prints a greeting. The ampersand str type means borrow a reference to a string slice. You'll see why borrowing matters in a second. If I run it, you see hello Rustacean printed on the screen. Let's talk about parameters and return values now. So I'm going to write a new function called square. Okay, so functions declare parameter types and return types. The arrow I32 means it returns a 32-bit integer. No return keyword, you don't need one for the last line. It's an expression. Rust doesn't use semicolons at end of return expressions, only on statements. So therefore you don't see any semicolon over here. Okay folks, let's talk about ownership. The single biggest reason Rust can manage memory safely without a garbage collector. It may sound complex, but the core idea is actually simple. So what is ownership? In Rust, every value has a single owner, the variable that holds it. When that owner goes out of scope, Rust automatically cleans up the value. Did you hear it correctly? Listen again carefully. When the owner gets out of scope, Rust automatically cleans up the value. No free, no delete, no garbage collector, just safe automatic cleanup. C++ devs think of it like everything in Rust acting as it were a unique pointer. When the owning variable goes out of scope, the memory is released automatically. We'll look at three side-by-side examples: moving ownership, borrowing ownership, and mutable borrowing. And we'll call all of them from main so you can see exactly how they differ. So to do that, let me get rid of this code over here. And we are going to start with move example. All right, let me write the function first, and then we are going to discuss it. All right, pretty simple code. Let's see what happens when we execute it. So if I do cargo run, we get a big fat error. Here's what's happening. We assign S1 to S2, but instead of copying, Rust moves the ownership. Now S2 owns the string and S1 is no longer valid. Rust prevents double freeze and other memory bugs by enforcing this rule at compile time. Think of it like moving a file on your computer. Once it's moved and you try to read the contents of files from the original source folder, it's no longer there and you get an error. By the way, I love Rust errors. They try very hard to make the concept sink in. Let's now see how we can pass values to functions as arguments while keeping ownership in the caller. Let me get this out of the way. All right, let's try it out first and then let's discuss. Oh, this one is causing the error, so let me fix this by typing S2. Okay, now everything worked. So you can see still valid after borrow working correctly. Here's what's going on. If you just want to use a value temporarily, you don't need to take ownership, like in the print length function, where you just wanted to print the length of the string. In this example, the function printLength borrows S1, it accepts a reference as a parameter by a ampersand string annotation. This lets it read the value without taking ownership, and S1 remains usable in main. If I rephrase it from caller's perspective, like the borrow example function, we pass a reference to S1 and the function borrows it over here. That means it can read the value, but it doesn't own it. Borrowing gives you read-only access to the data, and the original owner keeps full control. So what can you do with a borrow? You can read the value like we are doing on line 19. You can't modify it unless it's annotated with %mute, which we are going to see later. And you can't move it or free it because you're not the owner. Borrow example is. Again, for C++ developers, an %t in Rust is like a const t static, a const pointer in C++. You can look at the value, but you can't change it or delete it. However, if you want the function to be able to modify the value as well, we need to use the mute keyword again, but this time with the parameter declaration. Let me show you how. All right, let's try it out. And we see hello word being printed on the screen from borrow mute borrow example instead of just hello. And remember, comma word got added in the add word function. So what happened here? If you need to modify a value in this function, you use a mutable borrow using %mute. Looks pretty simple, right? But there's one caveat. Rust only allows one mutable reference at a time, and it must not overlap with any immutable references. You also can't read from the value while it's mutably borrowed, even in single-threaded code. Yeah, I know this technical definition didn't make sense at all, so I'm going to show an example. But first, let me tell you why this happens. Because overlapping access, even from the same thread, can lead to unexpected bugs or data races, just like it does in C++ and in such languages. Let's explain the issue by creating a borrowing error. All right, let's try running this code and see what happens. And it failed here. So as you can see, there's a thick error, version failed to compile, and here's why. We created a mutable reference R, but then tried to read S even before we used R. Rust doesn't care about order of lines. It sees that R is still alive and says you can't touch S while it's borrowed mutably. The point to remember is you can think of %mute like borrowing something with exclusive access. While someone else is using it, you can't peek or touch it, even if they are not doing anything at the moment. This avoids subtle bugs like race conditions or data corruption even in single-threaded code. So much for the problem. How do we fix it? Option 1, don't store the reference. Okay, so this is option 1 to fix it. We don't store the reference in a variable, so the borrowing ends as soon as the function call is done, right? For option 2, recall what I asked you to remember. When the owner goes out of scope, Rust automatically cleans up the value. So this is what we are going to use for option 2. Let me show you how. I'm going to again comment this part. Can you figure what's happening here? We limit the lifetime of R by putting it in the curly braces block. When the block ends, R goes out of scope, and Rust knows it's safe to use S as it kills R. For C++ developers, an %mute t is like a t-static or non-const pointer in C++, but unlike C++, Rust guarantees at compile time that you don't read from the value while it's being written, you don't write to the value while others are using it. That's the magic of Rust's borrow checker, like unique pointer plus const plus lifetime analysis, all built into the language. So as a final takeaway, a mutable borrow with %mute gives one part of your code exclusive access. While that borrow exists, no one else can read or write the value. The compiler tracks this not at runtime but at compile time. Result, safe, race-free code even with zero garbage collection. Now the $1 billion question, who cleans up the memory? So only the owner is responsible for cleanup. When the owner goes out of scope, Rust automatically drops the value. Borrowed references never clean up memory. They are just temporary access. In C++ terms, borrowed values are like raw or smart pointers that don't call delete. Rust manages all of this without you needing to write a destructor or track who owns what. That brings us to end of this section. Let's recap what we learned here. Each value in Rust has one owner. Moving transfers ownership. Borrowing gives temporary access without ownership. Only owners drop or clean up values. Rust enforces all of this at compile time with no runtime const. These are the rules that let Rust give you memory safety without a garbage collector. Next, we'll build on this with structs and enums, your building blocks for real data in Rust. Okay, folks, in this section, we talk about structs and enums in Rust. Let's talk about how you model real world data in Rust. Rust gives us two powerful tools for this, structs and enums. Let me type a struct first, and then we are going to discuss it. So a struct is like a blueprint. A struct in Rust is like a blueprint for a thing. In this case, a user. It tells Rust every user has a username, email, and an active status. It's similar to defining a class with public fields in C++ or a data class in Python. And if you're familiar with TypeScript, this would look very similar. Let's go over how to use it. Okay, here we access a new user by filling in all the fields. You access fields with dot syntax, user1.username, just like in JavaScript or Python. Let's make it even more interesting. Okay, this creates a new user by reusing the remaining fields from user1. This is called struct update syntax, and it's super handy for working with mostly similar values. But be careful with two things. First of all, if you are coming from JavaScript or TypeScript background, this is not the spread operator. It's two dots, not three, even though it's very similar. And secondly, fields like string get moved. So user 1 becomes partially unusable after this unless you are using references or clone. So if I execute this code, you see you are getting an example on email that value borrowed here after move. So user 1 cannot be used anymore. Let me get rid of it. All right, next, if you want to add behavior to your struct, you do that with an impl block. Let me type it first so you understand what I mean. All right, you might be wondering by now, why can't I write this function inside the struct itself, like in a class? In Rust, structs are only for data. Behavior, like methods, is always added separately using impl. This keeps data and behavior clearly separated and allows you to add methods in stages, implement traits like interfaces in other blocks, and keep your code modular and readable. The ampersand self parameter means the method borrows the struct so it doesn't take ownership, and you can still use the instance afterward. For folks familiar with object-oriented programming, impl is like a class body in C++ or Python, but split from the struct. It's as if struct equal to fields and impl equal to methods. Now let's see how a method is called. Let's try it out. And you see email is being printed down here. Now pay some close attention here. We call this method using dot syntax, just like Python or JavaScript, but method here is type safe. It looks like we are not passing anything here, but we actually are. Behind the scene, Rust automatically parses ampersand user as the first argument because the method takes ampersand self as parameter. So this line is actually a shorthand for, so you can think of self in Rust like this in C++ or Python. It's a reference to the current instance, and Rust handles that for you when you use dot syntax. I hope this is clear by now, and it would get solidified as you do more practice with it. Let's talk about enums now. So enums are used when a value could be one of several forms, right? This is not going to be clear without an example. So let me first show you how an enum looks like. So I say enum messages. So here we declared an enum. The message enum can be a quit, a move with coordinates, or a write with a string. Let me show you how it's used next. Alright, so here's the explanation for the code I typed. This enum defines a type called message, and it can be one of three things. Quit, which is no data, just a signal. Move, which has two named values x and y, like a mini struct. And write holds a single string. Unlike C-style enums, Rust enums can carry data, and each variant can have different types or shapes. Let's talk about process messages. Match lets us handle each variant of an enum in a clean, exhaustive way. Message colon colon quit matches exactly. Matches colon colon move destructures the fields so we can use them. And message colon colon write grabs the inner string text and prints the value to the screen. Main function puts it all together. In main, we create three different messages for each variant of the enum and then call process message with each. The Rust compiler guarantees each message is of the right type, the match logic handles all cases, and no need for nulls or flags or weird state checking. Let's execute this code and see it in action. Oh, sorry, my bad. It had to be curly braces here, not arguments. There were no arguments here. Here we go. Alright, to summarize it all, we use enums when our data can be one of several forms. Each variant can hold different types or name fields. Match lets you write clear, safe logic to handle each case. The compiler has your back, no missing branches, no nulls, no runtime surprises. And to summarize the entire section, we use structs to group data, we use impl to add methods, we use enums to represent different states or types, and we use match to handle enum logic cleanly. That's all for this section. Coming up, you'll learn how to store and manipulate collections like vectors and strings efficiently in Rust. Stay tuned. Now let's talk about collections in Rust, which are ways to store multiple values. The most common ones you'll use early on are vectors, which are used for growable arrays, strings for text, and slices for accessing parts of collection. So we are going to start with the vector example. So vex semicolon followed by square brackets is a macro to create a new vector. Vectors are like dynamic arrays. You can push new elements as long as it's mutable. And this portion in curly braces tells println to print using debug format, just like this. Let's see how to access vector elements. Alright, indexing works like in Python or JavaScript, but if you index out of bounds, Rust will panic, unlike Python, which returns an error, or JavaScript, which gives undefined. So let me show you a safer alternative. Okay, so instead of crashing when the index is out of bounds, .get returns an option. This means it might return some value or none, and Rust makes sure you handle both cases. This prevents bugs at runtime. You can't forget to check if something is missing. It's part of Rust's safety by default approach or zero cost safety model. Fail early, not silently. Let's now talk about strings. Strings in Rust can be a little tricky at first because Rust makes you think about ownership and encoding. So string colon colon from creates a growable owned string on the heap. Dot push str adds more text to it. Behind the scenes, Rust strings are stored as UTF-8 bytes, so characters might take more than 1 byte. That's why slicing them needs extra care. Right, so in Rust there are two main string types. String with capital S is an owned, growable string stored on the heap. Ampersand str is a borrowed string slice, a read-only view into a string. Think of string like a box you own, and $str like a temporary reference to read what's inside. So why most functions take $str as parameter type? Most functions accept $str like this because it's flexible. It works with string literals like Alice, and it also works with a string by passing the string with an ampersand sign. This avoids unnecessary cloning or conversions and keep your code simple and fast. Let's also talk about slices now. A slice is like a window into part of something. Here, an array. 1 dot dot 4 means start at index 1, stop before 4. So you get 2, 3, 4 being printed on the screen. And note arrays in Rust are zero indexed. Let's now see how we can slice a string now. You can slice strings too, but it only works if your slice lands on valid UTF-8 character boundaries. Otherwise, Rust will panic. That's because some characters like emojis or accents take more than 1 byte. So we need something safer than that. If you want to safely take the first few characters, not bytes, use .chars.take_n.collect. Here's what this actually does. .chars turns the string into an iterator. It walks through each full character, not each byte. .take3 grabs the first 3 characters. .collect puts those characters back into a new string with a capital S. This avoids slicing in the middle of a multi-byte character and works safely with any kind of characters, even emojis or accented letters, and keeps your code safe and clear. Alright, that brings us to end of this section. In all, we learned about using vectors to store lists of values, use string and $str depending on ownership needs, and using slices to reference part of the data efficiently. Next up, we are going to talk about error handling, one of the most unique and robust parts of Rust. You'll see how to work with result and safely deal with things that can go wrong.
Let's start talking about Rust error handling with something interesting. Rust doesn't have exceptions. Instead, it uses a type called results to handle errors safely and predictably. This forces you to think about errors upfront, not when it's too late. Right, this function returns a result. If b is 0, we return error. Otherwise, we return OK with the answer. Let's see how to call it. Match lets us handle both outcomes clearly, success and failure. This is how Rust makes you deal with failure explicitly. There is no panic or exception here. But note very carefully, even when you get OK, the value might still be invalid. Rust won't throw an exception, it trusts you to check it. For example, OK not a number or NaN is still OK, but maybe not useful. Always validate your results if needed. This approach just forces you to think about scenarios which may result in error. That's all. There are two related concepts, unwrap and expect. They are quick but risky. Let me introduce you to them. It's up to you to use them. But first, let's quickly see if this code runs. And if I do cargo run, we get error division by 0. Simple, right? All right, let's get rid of this. And next. So unwrap gets the value inside OK directly. But if it's an error, the program will crash immediately. Expect is just like unwrap, but it lets you add your own error message. This helps with debugging because you get a custom error message if it fails. Let's see what happens if I try it. Well, the top ones are just warnings because we didn't use the variable result and result2 in a println statement. However, this line 17 resulted in a division by 0 error, which crashed the program. It says process didn't exit successfully, right? But it did give you an error, which helps you with debugging. So the bottom line is use these in examples or tests, but avoid them in production code unless you are absolutely sure nothing will go wrong. Let's also quickly introduce the question mark operator. which results in early return on error. Here question mark is a shortcut. If the operation is okay, it keeps going. If it's error, it returns early with that error. Clean, simple, and used everywhere in real Rust code. By the way, in Rust, the open close parentheses used in OK are called the unit type. It's like nothing or void, a placeholder that means no meaningful value. In our example, it means the function succeeded, but there is nothing to return. All right, that brings us to the end of this section. So we learned here that Rust uses result instead of exceptions, use match for full control, use unwrap or expect when you are sure, but while fully knowing that they can crash your program. Use question mark to pass errors up in clean, readable code. Note Rust never throws exceptions, it makes you deal with errors safely and early. In our next section, we are going to see how Rust handles modules and project structure, so you can start writing clean, scalable code. So far, we have written everything in one file, main.rs, which is annoying to watch as much as it is annoying to do. But in real-world projects, you'll need to organize code across multiple files and modules. Let's look at how Rust does it and how it helps your project stay clean and scalable. So we're going to go ahead and change that now. So I'm going to get rid of all of the stuff over here and just leave a skeleton. And up top, I'm going to add mod greetings. Mod greetings tells us to look for a file named greetings.rs inside source folder. We are declaring a module here. Think of it like a subfile of your project. Now let's create a greetings.rs parallel to main.rs in source folder, and note the name must match. And that's it. We mark the function as pub, which stands for public. By default, everything in Rust is private, so this is required for main.rs to access it. Time to see if it works as expected. Right, saved both files and cargo run. Okay, I was talking about pub, but didn't notice it was not pub. This is fine now. Main.rs is good. Time to give it a try. So if I do cargo run, oh, I'm getting tired by now, right? Okay, here you go. Hello from a separate module. All right, so moving ahead, let's say we want to group related functions into a folder. For that, I'm going to create a utils folder inside source. Okay, and inside I'm going to create a file called mod.rs and just add a single line here called pub mod math. Very similar to how we had pub fun say hello, but this time we have pub mod math. Now I go to my main.rs and over here I say mod utils, and inside fun main I say right, where utils is our folder with mod.rs. And for math, let's create math now. So inside utils folder, I'm going to create a new file called math.rs and write some code. All right, you understand what's happening? In main.rs, we have utils colon colon math colon colon add, which is the call to our add function. And we only have an include file mod utils. In mod.rs, we have pub mod math, which is kind of making math module accessible from mod.rs. And in math.rs, we have our add function published, and it's simply adding the two parameters and printing them on the screen. Let's see if our code works first. And yes, it sure does. 5 plus 7 equal to 12. So what we just observed is a nested module. The mod.rs file acts like an entry point to the whole utils folder. If you're coming from other languages, it's very similar to index.js and JavaScript module folder or underscore underscore init.py in a Python package. It tells Rust this folder is a module and lets you expose other files like math.rs from inside it. I hope this made sense as we are at the end of our chapter. So summarizing what we did here, we use mod to declare modules, we use files and folders, mirror your code structure, use pub to expose functions, and we saw how to nest modules to organize larger code bases. Next up is the exciting part. We'll build a small mini project to reinforce everything you have learned so far. Now that you have learned the Rust basics, that is variables, functions, control flows, structs, enums, ownership, etc., let's put it all together. We are going to build a real Rust project from scratch, a reusable math library with a CLI front end. You'll see real world structure like multiple files and modules and how to start thinking in terms of libraries, not just one-off scripts. So first off, let's create the project. Note that dash dash bin creates an executable with a main.rs. This is perfect for our CLI entry point. Let's open it in Visual Studio Code using code dot. Now we'll add a lib.rs too, which is where we'll put the reusable logic. All right, now inside source, let's create a folder called math for the math related logic. In here, we need to create a mod.rs file and another file called operations.rs to hold our functions. Right now in source lib.rs, we need to declare the math module. And now inside source math mod.rs, we wire in the operations module. Perfect. Now we go to operations.rs and add some basic functions. Okay, these functions are basic, but we are already thinking in terms of clean, testable, reusable library code. No user input, no side effects, just pure logic. That's what makes this code powerful and portable. Lib.rs acts as the entry point for all library code. It's how we export our logic so it can be used by main.rs or even by WebAssembly later. You might be wondering, earlier we used result F64 and string for error handling, so why are we using option F64 over here in divide function? It's because this is a WebAssembly ready project, and when compiling to WebAssembly, returning a full result with a string error message adds extra complexity we don't want in a beginner course. This keeps the project clean, easy to follow, and compatible with both CLI and WebAssembly without extra setup. And don't forget, this is a crash course. We are focusing on the core ideas without getting lost in edge case plumbing. You'll still be writing real Rust, just without the extra pain which is out of scope. Now let's go to main.rs and write a CLI to interact with these main functions. Alright, this is the entire code. You don't need anything fancy here, just basic IO, pattern matching, and logic reuse from your library. All is missing at this stage are required imports at top of main.rs. So let's add those. So if I go here and say use stdio for IO related operations and use lib math operations. And we should be good to go. Let's
test this out. So if I bring up do cargo run, yeah, some error had to occur. All right, match arms have incompatible types. Okay, so expected option F64 for option F64. All right, line 27 has some issue. Some operations divide. If I go to operations.rs, all right, here's the problem. We are doing sum over here and we are doing sum over here again. So these two are combining to give us a headache. So I'm going to remove one of these sums from over here and let's try it out again. So CLS cargo run, and this time it's working. Choose an operation, add, subtract, multiply, divide. All right, let's try with subtract. First number 10, second number 3, result is 7. All right, let's also check with divide. 15, 5, and result is 3. So we have got a working CLI mat tool built in Rust. So far, we have been working in the terminal, building a CLI in Rust. But what if I told you this exact project could also run inside a web browser? That's where WebAssembly comes in, a way to compile Rust into something that runs alongside JavaScript in the browser. Why is this exciting? Because Rust is fast, really fast, and WebAssembly lets us bring that performance to the web safely and portably. You are no longer limited to just JavaScript in the browser. With WebAssembly or Wasm, you can write high performance Rust code and use it right on a web page. And here's the best part. The way we have written this project, with logic separated in operations.rs, it's already WebAssembly ready. You don't need to change a thing. This structure means we can reuse the exact same code for both terminal and browser apps. In fact, for those viewers who have already seen our Rust plus WebAssembly Hello World video, you have seen how simple it is to get started with Wasm. That video covers the basics, setting up Wasm pack, exporting functions, and calling Rust from JavaScript for viewers who have not worked with Rust before. So while I work on a follow-up video showing this exact library in a browser, you can already start experimenting thanks to how this project is organized. And because we used option F64 instead of result F64 in divide function, the math functions are already WebAssembly friendly. No extra setup, no serialization headaches, just clean Rust ready for browser or terminal. So by now we have built a modular Rust project that has clean separated logic, runs in the terminal using standard Rust tools, and is ready for reuse in WebAssembly or even as a crate in other Rust projects. In the next video, we'll take this exact math library and compile it to WebAssembly so we can run the same Rust code inside a web page. No node, no server, just Rust. Compile to the browser. Stay tuned for that. But before we wrap up, let's take a quick look at how Rust projects work in the real world with cargo and external libraries called crates. Think of Cargo as Rust's all-in-one toolkit. It builds your code, manages dependencies, runs your program, runs tests, and even generates docs. Everything you need is built in. Let's try out a few commands which are listed on this cargo book on docs.rust-lang.org/cargo. So here's the full list of commands over here. We are going to try a few of them. So let's open our terminal and start with cargo build. This builds our project. Oh, there's an error on line 27. Oh, you remember we removed the sum from the divide, so that's what it's complaining for, that we left the parentheses around it. So quick fix here. And the compile finished. Pretty fast, wasn't it? All right, and it created this target project with all of our output. The next command to try is cargo run, which executes our project. So you are already familiar with that. It launches our CLI. And so we can do operations like add, like 3, 4, and result is 7. We have already gone through that. The next is cargo check, which does a fast type check without compiling, pretty fast and pretty useful in day-to-day work. And the last one, cargo doc dash dash open. This one is especially cool. Cargo doc gives you full documentation for your project and any crates you use, searchable and in your browser. So let's say if I go to Rust Math Lab and click Math Operations, it gives you documentation for all the functions. And you can also search for that. So if I had just searched for divide, I would have seen something like this with option to filter on a particular crate. Our next topic is using external crates or third-party libraries. So in Rust, third-party libraries are called crates, and you add them by editing your cargo.toml file. So let's try something fun and visual, coloring terminal text. For that, we are going to use an external library called colored. But before using any external crate, you first need to find it. The place to discover and browse Rust libraries is crates.io, Rust's official package registry. Let's search for a color crate here. So I'm going to search for colored. It's a popular one for terminal styling. So I'm going to open it. Now, the next step is to add it to your cargo.toml file. You can also use cargo add colored command, which is given here, or you can simply copy it from here and paste it under the dependency section of your cargo.toml file. That's what we are going to do. Next step is to use it in your main.ts. So the documentation is available here in the how to use section. There are steps you need to take. So we are going to use these steps. So I'm going to go to the top and say, in fact, let's not mess up this project. Let me cut that from here and go to a previous project, paste it here, go to main rs, get rid of this, and use colored colorize as suggested on this colored library page. And in fun main, I'm going to say, or just copy and paste. Why not?
Let's execute and see using cargo run. And it works. You see works is in blue, just as we expected. Let's make it even more better. So I'm going to get rid of this. Okay, try again. Awesome. This create gives you extra methods on strings like green or bold to make colorful terminal apps, easy to use and fun to try. You can use it to color code your output like error messages, warnings, and success messages in real projects. Note crates.io should be your go-to resource for practical libraries like this one. When you click on a crate, you should make a habit of checking its usage or README section. It often tells you exactly what to put in your cargo.toml and what to use in your code. Right, this brings us to the end of crate and cargo section. So now you know how to build, run, and document your Rust project, how to add external crates from crates.io, and where to find crate examples and how to use them. And that's it. Your Rust crash course is complete. You've covered a lot: syntax, ownership, enums, modules, building a project, and using crates, all in under 1 hour. If it feels exciting but fast paced, don't worry. We'll build on this in future videos, including compiling your Rust code to WebAssembly and embedding it right into a web page. If you're just starting, don't forget to watch our WebAssembly with Rust Hello World video. It's very beginner friendly and would be a great start. I'll leave a link in the description. If this was helpful, do give it a like, leave a comment with what you want to build with Rust next, and definitely subscribe so you don't miss the next videos in the series. We are just getting started. See you in the next one. Thanks for watching. Goodbye.